states, and in fact I will mostly talk about Topos quantum logic aspect and very little about mixed states, just towards the end of my talk. Much of it is joint work with Chris Isham, and there's some new results, and actually I intended this talk to be easy in the sense that it's not overly technical. Probably I failed again, but it's very much about saying what kind of structure you may see in quantum theory if you look at it from the perspective of the Topos approach. The Topos approach is something that was initiated by Chris Isham and Terry Butterfield 11 years ago now, and I've been working with Chris for slightly over 3 years developing this, and let's say the logical aspects, they are just a part of a bigger story. But since this is a workshop on quantum physics and logic, I thought it might be nice to say something about that. No signal? No signal.
Hit escape.
Hit escape. Just open it and close it. And yeah, okay. So, name. This one?
No, it must be, it's this talk here. It's directly in the main lecture, yeah. That's
You.
okay, thanks. Yes. Yes, some people have said they're not physicists, so I'll tell you what physics is all about on my first slide. Physicists think about the world as divided into systems, and each physical system, S, comes with a collection of physical quantities, A, and we assume that these physical quantities have real values. And at a very basic level, physics arguably is about what can we say about the truth values of propositions of the form A is in delta, which means the physical quantity A has a value in the set delta of real numbers. And of course, I can only say something about truth values in any, I must have a state of the system given. So that's what physics is about, arguably. In classical physics, which is a realist theory, there's no problem. In any given state S, all physical quantities have value, all propositions have truth values. Of course, these truth values are true or false. And, well, how are propositions represented in classical physics? Well, they're represented by measurable subsets of the state space. And, well, these measurable subsets, they form a sigma-complete Boolean algebra. And pure states are represented just by elements of state space. In quantum theory, of course, is very different. Propositions are represented by projections or equivalently closed subspaces of Hilbert space. And pure states are given by unit vectors in Hilbert space. And say psi proposition has a probability of being, it's just the expectation value of the projection representing the proposition. So this is a real number between 0 and 1. And the projections form a non-distributive lattice, as is well known. So the meter and the join, they don't distribute over each other. Nonetheless, Berkoff and von Neumann suggested in 1936 to consider this lattice as representing propositional quantum logic. And this comes with a whole bag of well-known conceptual and interpretational problems. I think most of you will know this, and if not, then there's not enough time to explain this, unfortunately. What I want to do is to talk a little about a novel form of quantum logic, which is based upon the use of a certain topos. We do not need much topos theory. The basic idea, this is actually what can serve as a guiding light for the whole talk, is that if you formulate quantum theory in a suitable topos, it looks like classical physics. It is structurally similar to classical physics in many respects. In particular, with respect to what you can call logical aspects, or representation of propositions, algebraic structure of propositions, states as truth value assignments, all these things look somewhat similar. And this is what I want to show. How is it done technically? In Jeremy and Chris suggested to take the Kochen-Specker theorem seriously, and this suggests contextuality, which is a somewhat, well, let's say, not undefined, but over-defined notion. Many people understand different things by this, but we very specifically understand the following. We consider the partially ordered set of abelian von Neumann subalgebras of all bounded operators in Hilbert space. I should say at this point that we can do this for an arbitrary von Neumann algebra, so it can be done much more generally, but I don't want to overburden the technicalities of von Neumann algebra, so we basically look at BFH, and you can generalize without extra effort. And these abelian subalgebras are called contexts. And each context is something like a classical perspective on the quantum system. And then there's a bit more structure, because we do not just look at the subalgebras themselves, we also regard them as a poset. So we know when a small algebra is contained in a larger one. So let's say V prime is contained in V. Then V prime contains less self-adjoint operators and less projections. So very roughly, you can describe less physics from the perspective of V prime than from the perspective of V. And this poset structure is interesting for another reason. If some algebra V prime is contained in two different algebras, V1 and V2, this of course does not imply that all operators in V1 must commute with all operators in V2. So commutativity is not transitive in that sense. If you have if you have two algebras, V1, V2, their intersection will be such a V prime. But this by no means is equivalent to the fact that V1 and V2 only contain commuting operators. The projections in each context V form complete distributive lattice, denoted as P of V, and the emphasis is on distributive here. So there's no interpretation problem whatsoever looking from the perspective of a single context. And of course these projections, they correspond via the spectral theorem to propositions about physical quantities in V. And each V is uniquely determined by its projections because the von Neumann algebra is generated by its projections. Instead, we want to consider structures over this partially ordered set of all classical perspectives. We want to have all these partial classical perspectives, we want to take them all together, and we want to build structures over them. A very simple-minded thing you can do is actually look at set-valued functors, and for several reasons I can't go into here, but I can say a bit more after that talk if you like. We choose contravariant functors. So we look at contravariant set-valued functors. This is really embarrassing. I have used the wrong macro. This should be V of H instead of B of H all the while. So actually, the base category is of course the partially ordered set of abelian subalgebras. So somehow this slipped in because I changed macro. So anyway. This pre-sheaf category actually is a topos. There's all this extra structure that makes it into a topos, and we don't have to go into this. For us, the main point is that each object P, each pre-sheaf, this is the name for these contravariant set-valued functors, can be seen as kind of a generalized set. So, I mean, I suppose everybody knows what a contravariant functor is. So, you know this, but really think of the guys in that category as generalized sets. In the following sense, for each context V, there's one set, PV, so I assign one set to every context, and if I have such an inclusion, then I have a function from PV to PV prime. So the arrows reverse because it's contravariant functor. Of course, everything has to fit together nicely to form a functor. And like every topos, our pre-sheaf topos has an internal logic. And this logic is multi-valued. And the truth value in the internal logic of our topos is actually nothing but a lower set in this context category. So as a partially ordered set, you know what a lower set is. So if you have some V is contained, then everything below V is also contained. So that's how these truth values look like. And because there are infinitely many contexts, you can easily see that there are also infinitely many truth values actually in this internal logic. And this internal logic, as is typical for Topos, is intuitionistic. Means the law of excluded middle does not hold, but the distributivity law, for example, does, in contrast to ordinary quantum logic. And so we want to use this logical structure in quantum theory. Okay, we need one piece of structure, one thing which is very important in the whole theory, and this is an analog of the state space. And this is constructed in the following way. If you have an abelian phenomenon algebra, then this is isomorphic to the continuous functions on its own Gelfand spectrum. The Gelfand spectrum is denoted as sigma v, and this is a compact Hausdorff space, and since we have phenomenon algebras, actually have extremely disconnected spaces. Topologically, this is not, well, it's just how it is. The main point here is that the Gelfand spectrum is like a state space locally at V, because I can write physical quantities anywhere in my self-adjoint operators in V by real-valued functions on this compact Hausdorff space. Then we define a pre-sheaf in the following way. We assign to each abelian subalgebra V its Gelfand spectrum. Whenever I have an inclusion of V prime into V, I have this canonical function. I just restrict the elements from the larger Gelfand spectrum to the smaller one. Well, the elements here are algebra homomorphisms from V into the complex numbers. This is one way of looking at them. So of course you can restrict to the smaller algebra. And this, of course, is a pre-sheaf, so it's one object in our Topos. It's a special object in our Topos, and it's built from all these local state spaces. And this is the analog of the state space. Okay. Now we take this idea seriously that we have something like a state space with this kind of a generalized set, so we construct subsets of this thing, and this will actually be sub-objects or sub-pre-sheaves that represent propositions. So we start from such a proposition, A is a delta, and let P be the corresponding projection via the spectral theorem. And then for each context V, I define what you can call a coarse-grained projection. I simply approximate P from above by the smallest projection in V, larger than or equal to P. In the level of propositions, this is the strongest proposition implied by A's and delta, which is available from the perspective of V. So I adapt the proposition to all these classical perspectives that I have. Then there's one piece of, well, the piece of structure we'll use all the while. We're talking about projections at this moment. But in each abelian phenomenon algebra, I have a lattice isomorphism between projections in V and the Klopen subsets of the Gelfand spectrum, so closed and open. It's given in that way, so this is something that I will use constantly to switch between projections in V and Klopen subsets of the Gelfand spectrum. Okay. Then I define what we call the Daseinization of projections. It's the following mapping. It's a mapping from the projections to the Klopen, or I'll explain this notation in a moment, to two sub-objects of sigma. It's given the following way. You send P to delta of P, which of course is given, well, such a thing. Actually, it is a sub-pre-sheaf, so it has components. For each V I have something. And the something I have is just the Klopen subset corresponding to this coarse-grained projection operator. So I approximate the projection in every context, and then I go to the corresponding Klopen subset, and then I collect all these things. It's easy to see that I get a sub-object of spectral pre-sheaf, and well, of course, each component is a Klopen subset by construction, and we call sub-objects such that every component gives me a Klopen subset. We call them Klopen sub-objects. And this is somewhat similar to the classical case where you will not want to talk about all subsets usually of state space, but you want to talk about measurable ones. So the cloak and subobjects are something like the analog of measurable subsets. The cloak and subobjects, as proof needed, they form a complete Heiting algebra. And this is what you write this way, sub C over sigma. Yes, as I said, this algebra is the analog the Boolean sigma algebra of Borel subsets of the state space for a classical system. And how are meets and joins defined in this letter? Well, they're defined stage by set theoretic operations. And for example, if I have two subobjects S1, S2, and their meet is defined, well, at V, I just take the set theoretic intersection. For infinite meets and joins, I must take a little care to stay among cloak sets, and I have to take the interior, respectively, the closure of the set theoretic union, but that's not important for what we'll look at. So via the correspondence, A is in delta, goes to P, goes to delta of P. The cloak subobject delta of P represents the projection A delta. So we have now represented this proposition. So it's a proposition A is in delta. So we have represented the proposition by something which is, well, like a subset of state space. So it's a sub-object of our state object, the spectral presheaf. But it doesn't make sense. I mean, I want to say a few things about the properties of this mapping, and there might be some new aspects. Some people have heard these things before quite a few times, but there's some new aspects, I hope. So, first of all, it's very easy to prove these three things. This Dazonization projections is an order-preserving mapping. It is injective, and the null projection goes to the empty subobject, and the identity goes to the whole of sigma. So obviously all these things make sense if we interpret this physically as we intend to do. Here's a lemma. Actually, I include the proof, but I think I don't have time to go through it. The lemma says that for all projections P and Q, it holds that delta of P or Q is delta of P or delta of Q. So Dazonization projection preserves the or. And this is actually an interesting aspect. The first sentence on this slide doesn't make sense, because it should of course be the join of projections is interpreted phenomenologic as the disjunction of the corresponding propositions. So just swap the words projections of propositions. So I argue what people do in standard quantum logic. This is when we talk about projections, and that's okay. If you have the join of projections, this corresponds to the disjunction of corresponding propositions. And this relates very much to superposition. And why is that? Well, the join of projections on the level of subspaces, of course, corresponds to the span of the subspaces that these projections project onto. And there may very well be vectors in the span which do not lie in either subspace. So there will be states which make the proposition represented by the join true, while these states do not make either of the propositions represented by P or Q true. And interestingly, we see that Dazonization preserves this junction, and hence that aspect of quantum logic that relates to superposition. And truly this is a pretty fundamental thing in quantum theory, so well, it's just there. And even more interestingly, we tend to think that superposition is, well, closely linked to the linear structure of the theory. But here, neither the spectral presheaf nor its components are linear spaces, and still this piece of structure is there. And actually it's something so simple like set theoretic union, stage by stage. So I find this an interesting aspect of the story. What about conjunction? Well, standard quantum logic is often criticized for the fact that you have conjunctions of arbitrary propositions, including those which are called strongly incompatible, like, well, the spin in x direction is up, and the second projection is spin in y direction is down. Many people say from physical intuition, the end of these two propositions shouldn't be defined at all, because semantically it doesn't make sense. Well, we do have arbitrary conjunctions in the Topos quantum logic also, but there's a new aspect to it due to coarse graining. Maybe it's the following. So let V be a context which contains a projection P that represents the spin in x directions up. Since Q does not commute with P, the same context V cannot contain Q, so this mapping delta O, this approximation, will make Q actually larger when I look at it from the perspective of V. Similarly, if I look at a context that contains Q, then I must adapt P by making it actually larger. So, somewhat intuitive interpretation of this is that incompatible propositions are not expressed from the perspective of any single context. But nonetheless, the sub-object that I get from this, basically I was looking at components of this, but now I look at the whole sub-object, it's the global thing that's still well defined. And it's easy to show that, well, the conjunction is not preserved, delta of P and Q is smaller than or equal to delta of P and delta of Q. This also leads to something interesting. Don't know if I have time today, probably not. You can have sub-objects which represent propositions, for example, such conjunctions, which are not totally true in any given state. This is different from ordinary quantum logic. Okay, a few words about states and how do we represent them. First of all, pure states. Let psi be a pure state, and we look at a certain pre-sheaf representing this. It's actually very simple. For each V, you just look at all those Cloten subsets such that the corresponding projection is larger than the projection given by the state. So P is greater than or equal to P psi, and then I use this isomorphism between the less of projections and less of Cloten subsets, so this is coming into the game here again. Then I can go from T psi V to T psi V prime just by sending SP to S delta of P. This gives me. Actually, I'm simplifying somewhat. The papers well, I would call this the truth object. Actually, the truth object is a power object, so it's slightly more complicated than this guy, but this is enough to see how it works. So basically, at every stage V, I collect all those P's representing propositions I can make from the perspective of V, which are true in the state P psi. This is just the condition for them to be true. The global elements of this pre-sheaf are Cloten sub-objects that represent propositions which are totally true in the state psi. So what does this correspond to in the classical picture? Because I said it's all analogous somewhat to the classical picture. Well, it's very simple. If you have a state of the classical system, you can look at its neighborhoods. They represent propositions which are true in the state. And this T psi is just the analog of that. So what's the analog of the point itself, if you like? Well, it turns out that this pre-sheaf sigma has no points in the sense that it has no global elements, but still this collection here has the smallest element. So it has something which is as good as we can get, as close to a point as we can get in this picture. So the smallest Cloten subobject representing a totally true proposition is just given by, well, the Dasonization of P psi. And we call this the pseudo-state associated to psi. This is actually an analog of a point of state space. So how do we get truth values? Well, in classical physics, the truth value for proposition is given in a very simple way. You represent the proposition by some subset of state space, represent the state by, well, it's an element of state space, and you basically ask, does the state lie in the subset, or does the point lie in the subset or not? And that's your truth value. And we are doing just the same. It's really that simple also for this seemingly much more complicated setup. In quantum theory, the truth value of this proposition is also given by asking, does something lie within, well, does the thing representing the state lie within the thing representing the proposition? So we saw that the state is represented by this W psi, and the Cloten subobject S represents a proposition. So the truth value of proposition represented by S in the state psi is just this valuation. It's a collection of all those contexts V such that, well, this component is contained in this component. So it's exactly the same kind of question we're asking here. And it's very easy to see that this gives us a lower set in the context category. So this is nothing but the truth value in the internal logic of our topos. Well, in the classical case, you just had two possibilities, either S does lie in S or not. Here you have more. But the truth value is, if you like, the degree to which the proposition represented by S contains the smallest totally true proposition represented by W psi. And since we have a lower set in this context category, you can ask for every V, does it lie, well, is it contained in the truth value or not? So locally, for each V, you get either true or false. And things fit together globally to form such a lower set.
5 minutes, Andreas.
Yeah. Okay, thanks. Yes, mixed state. So actually, I'll say a few words on mixed state. Well, a general state of a classical system is a probability measure of the state space of the system. The general state of a quantum system is a positive linear functional row on our algebra. So seemingly very, very different things. But in the Topos approach, we can do the following. We can describe every state by a measure on sigma in the following sense. We define a measure mu rho associated with the state rho as a mapping from the closed sum-objects, and here it comes into the game that they, as I said before, these guys are like measurable subsets. So this is what explains the domain of the measure. In the codomain, this is, well, it's a certain piece of notation. This actually is global elements of a certain pre-sheaf, but something very simple. You have functions from the context category to the unit interval, and they are antitone. So if you go to a small algebra, the numbers can only grow. And it's defined in that way. You just, well, for every global subobject, you just do the following. You evaluate the state row on the component at V, and you do it for all V's. And so you get such a value. And you can do this abstractly. You can say a measure is just such a mapping with only these two conditions. Well, the whole of sigma goes to the function that's constantly 1, and I have this condition which is very typical for behavior measures. And these are very weak conditions, arguably. So they know nothing about non-commutativity. They know basically nothing about linearity. So very weak conditions. And interestingly, one can show that if your whole space is at least three-dimensional, then there is a bijection between abstract measures and states rho. And again, this result holds much more generally, holds for all phenomenon algebras without a summand of type 1, 2. So what really does the work at the end of the day is the generalized version of Gleason's theorem. But still, it's a nice thing. So we can think about arbitrary states of a quantum system as probability measures. So again, it's an analogy to the classical case. So how does it relate to the logic? Well, if you have a pure stating, and we're going to talk about pure states for a second, we can of course also associate a measure to that. Then the support of the measure, the smallest closed subobject that gives, well, is of measure 1, so gives constantly 1 for every context, is exactly the pseudo-state, which I said is like a point state space. So there's a nice relation in that respect. And more generally, I can calculate the truth values also from the measure. So this is also a nice thing. It's also very simple, actually. If you think about it for a second, you would not expect that for mixed state it's just as simple. The pseudo-states won't take you very far. There are connections between the measure theoretic and the logical aspects, but not quite as straightforward. But what you can do is generalize the notion of the truth object that we had. And instead of having just one truth object, we now have a whole family of them indexed by all real numbers between 0 and 1. It's defined in the following way. And the intuitive idea is that each T row R is a pre-sheaf over the context category. So if you fix R, you get a pre-sheaf. And this pre-sheaf has as its global elements all closed subobjects that are of measure constantly r or greater. Obviously every state row gives you such a guy, and one can show that you can get back to the state from such a family. This may lead away to purely logical description of arbitrary states if we do this in a suitable topos. The summing up, we get a new form of quantum logic that has these nice features which are all different from standard quantum logic. There is a clear underlying geometric structure in the form of the structure pre-sheaf. The Doesonization, which is kind of a translation mapping between standard quantum logic and in this form that behaves sensibly, physical interpretation. States give us truth valuations in a very straightforward way, and mixed states also fit in there in this future work. Finally, I want to say something about related work. Hansmann and Chris was also one of the authors, proposed a closely related form of Topos quantum logic, but based upon covariant functors over the context category. And there you have actually that from the external algebra you obtain an internal abelian algebra which has a Gelfond spectrum, and then the idea is to regard opens in this locale as representatives of propositions. And a few years back, Bob has proposed a framework for quantum logic in a mutualistic perspective, and he uses construction which I understand was found in lattice theory without people thinking of physics, but called the injective hull of mean semi-lattices, and he actually reinvented that. And what's done there, you embed a mean semi-lattice propositions into complete Hating algebra. This is quite different in most respects, but both frameworks, the Topos framework and this one, of course, have a complete Hating algebra, so there's kind of underlying geometric structure.
It was worse that I reinvented that with PhD student of Bruns who's here. And I didn't realize that his supervisor already did that.
Okay. Anyway, so if you want to read a bit more about this, you can find it here and of course in the conference proceedings.
We really have time for questions now, I'm afraid. I'm sure Andreas will be around for the rest of the evening. If we could have our next speaker up. Thanks for speaking.